السلام عليكم ورحمة الله وبركاته. حياكم الله جميعا. نكمل اليوم دورة هندسة ريمان في يومها الثالث مع الدكتورة ليانا عضو هيئة التدريس في جامعة الملك سعود، فلتتفضل. Welcome دكتورة ليانا.
Thank you. So hello, we are going to continue today. This is our last lecture. Tomorrow your instructor will change. So we are going to start talking. So remember that I told you yesterday that our goal today is to integrate all manifolds, to present that Stokes theorem and give some applications. But for this we need to build up all the notions that we need for this. So we are going to start today with a little bit of algebra, and we are going to see what is first the exterior algebra. Well, suppose that V is a vector space, and then you take a map defined on a Cartesian of V copies of k copies of your vector space with real values, which is multilinear. So on every component, the map is linear. I wrote here what this means, and that satisfies this last property, namely, if you interchange two consecutive arguments, two consecutive vectors there, then you get a minus in front of. So there is a minus coming out. Now, the space is something like this is called an alternating K form on the vector space V. And if we take together all the alternating K forms, we denote this by this lambda K V star, and this is called the kth exterior power of V star. So it's pretty immediate that the one exterior power, the first exterior power of V star will be V star, and we just let the zero power to be R, the set of real numbers. I'm going to go as I like on a white page. So okay, so we are here, right? So what we said is this: we have a vector space. Now you know what is V star. This is the algebraic dual. Here you have all the maps that go from V into R, which are linear. This is the algebraic dual. And then we denote by lambda K of V star the kth exterior power, and this means all the maps which are defined on V times V K times, real valued, which are multilinear, so linear on every component, and such that omega of, so here, when you switch two consecutive vectors, this is minus omega of, so here you have Vi plus 1 first, Vi, and then everything else. All right, now, what would be, okay, all right, what would be the first exterior power? So, okay, something's wrong again. All right, no, it works, sorry. So what is this? So we have maps going on V, just one copy of V over with values in R, which are linear, and well, the second condition is not there anymore because you only have one component, so linear. So you see, this means precisely the algebraic dual of V. And we say that the zeroth power is the set of real numbers. All right, and now we are going to see we are going to define some operation here, and we are going to define the so-called wedge product or exterior product, right, to be a map going from the K exterior power times L exterior power into K plus L exterior power of V, in which we take here we take a K alternating form and a L alternating form, and well, we are going to get something here, so K plus L alternating form, and we are going to define it like this. So alpha wedge beta on V1 So we are here, so we need k plus L arguments here, and we define it to be sigma, so sum of signature or of sigma, and I'm going to explain what this means. These are the KL shuffles of the set 1 up to k plus L. I will explain. Then the first, so alpha applied on the first k term, sigma of 1 up to sigma of k times, remember that these have real values, so this is a real number, times beta of v sigma v applied on sigma of k plus 1 up to v of sigma of k plus L, so on the last L components, right? This is correctly defined. Now, this simply means, so this is the set of KL shuffles of 1, 2, up to k plus L. This simply means that you take a permutation of the set 1 to up to k plus L such that the first k values are increasing and the last L values are increasing as well. So it's something like this, okay? Now, so this is called the wedge product or the exterior product, and we have a simple remark here is that if A belongs here, so to remember this was assigned to be R, and alpha is a is an alternating K form, something like that belongs here, then wedge product between A and alpha is simply A times alpha. This is a real number, right? So this is the same as this one, right? So this means simply a product between the number and between a real number and alpha. I'm going to take some examples here to see that we understand how this wedge product. So suppose that you have, for instance, alpha and beta alternating forms here, right? Then what will be alpha wedge beta? So first of all, this must lie here, right? 1 plus 1. So this is what? This is something defined on the Cartesian product v by v twice, right? So with real values, and the alpha wedge beta, so it will apply on a pair of vectors here, v1, v2. So now the definition is here, all right? So it's the sum of all, so you apply alpha on a vector, beta on another vector, and then you need a signature coming from the permutation. So if you look at the permutations of 1, 2, you have two permutations here, 1, 2, and 2, 1, right? These are the permutations for the set 1, 2. And now the first one must be increasing. Well, it's always increasing, one term with a single, one segment with one single term, and the second one increases. So the same, so both permutations act here. The signature here is 1. Signature means -1 to the number of inversions, right? So you just count how many inversions you have. So here you have one inversion. You see 1 is smaller than 2. It comes after 2, right? This means an inversion. So you have a minus here. So this wedge product will be alpha of v1 times beta of v2. This is the permutation with plus here. And then we have another one, this one, so you'll have an alpha of v2 times beta of v1, and the sign is this one, okay? So it's something like that. Now, what will be, for instance, say you have an alpha, a two alternating form. Let's just get an example a little bit more expanded, and beta, again, a two alternating form. So let's see what is alpha wedge beta. So this, first of all, this will lie here, 2 plus 2, that's 4. So you'll apply it on 4 vectors. So v1, v2, v3, v4. All right, so now we need to do what? So it's 2 and 2, right? So you will have all the permutation of 1, 2, 3, 4 with all the two shuffles, we say. So with the property that the first 2 images here are increasing number and the last 2 are increasing. So for instance, the identical is good. Then another permutation 1, 2, 3, 4. So I'm going to keep here 1, 3, 2, 4. You see, if you look at the first 2, this is increasing. This is an increasing segment. This one not take, then the only key which is the one some permutation that we didn't talk about yet. So then here you must have 2 and you must have 3, right, to get it increasing. And then you will have, we finish with 1 on the first position. So let's look here at 2. This must be increasing. So you have a 3 or 4. So you have a 1 or 4 here, then 1, 2, 3, 4, 1, 4, and then this will come with 2 and 3. 1, 2, 3, 4. We finish with, sorry, this is 2. This is 2, 4, and 1, 3. We were at 2. Then let's put here 3. The only increasing is 4, and this one increasing will be 1 and 2. So you have six possible cases. Now this will have a will come with plus. The signature is positive. This will be negative. This will come with a plus. You count the inversions and you get an even number. Then this will be positive. Then this will be negative, and this will be positive. Okay, so when you write them down, so this one will be alpha of v1, v1 and v2 times beta of v3 and v4. Then this one will come with minus alpha of v1 and v3 beta of v2 and v4. And here, right, this will come with plus, so it's plus alpha of v1, v4 beta of v2, v3. Then I'm here, this comes with plus alpha of v2, v3 beta of v1, v4. I'm here, minus alpha of v2, v4 beta of v1, v3. And finally, this one, positive plus alpha of v3, v4 beta of v1, v2. So I think now it's pretty clear how we calculate the wedge product of alternating forms. All right, and now the wedge product has some nice properties. Okay, we are here. So we did this. So we are here. The wedge product has some nice properties. So I'm going to skip the first one because we didn't talk about the interior product. It's here presented on these papers, but it's not very useful today, so I skipped it. The wedge product is, so we say that it's graded commutative. So when you compute the wedge product between alpha and beta, then that's -1 times to KL beta wedge alpha. K and L are the the degrees of the forms. The wedge product is associated, so alpha wedge beta wedge gamma will be alpha wedge beta wedge gamma. And then the nicest part here is that we can write down the dimension of these spaces, and the dimension of the cave exterior product of V star is n choose k when k is between 0 and n, and is 0 if you have more vectors than the gray, so when n is less than k. And we even have a basis of the cave exterior power, which is given by this wedge product E1 wedge E2 up to EK, where E1 up to EK is any k tuple of increasing indices from the base. I'm going to explain this a little bit. So we have something like this, right? So suppose that you have your k exterior power, and now suppose that V is a vector space, finite dimensional vector space, and you have a base dimension n, so the dimension of V n, and suppose that we have a basis here. I'm going to denote it by something like this: basis for V. Now, every basis for V will determine a basis for the dual space. So the dual space V star will have the same dimension, and you will have a dual basis here. E1, I'm going to denote it by something like this. This is the basis for V star, is the dual basis. And now, a basis for the cave exterior power of V star is given by something like this. E I1, so I'm taking vectors of the basis of V star. So you are edge product EI2, wedge product EIK, where this sequence is increasing. Okay, so something like this. I'm going to write down an example so you understand it better. So you see, because we have a basis here, then we can find the dimension of this space. What is the dimension of this space? The number of the vectors from the basis. So the dimension of the kth exterior power of V star, in how many ways? So how many vectors do we have in total? N vectors. How many do we need? We need k, right? So the dimension will be given by n choose k. In how many ways can we choose k vector and increasing, right? Sequence of k numbers out of n numbers. This is n choose k when k is between 0 and n, and will be 0 when n is greater than k. Okay, so now as an example, let's write down a basis here. So let's say write a basis for the third exterior power of V star if the dimension of V, which is the same as the dimension of the algebraic dual, is equal to 5. So we have a 5-dimensional vector space, and we want to write down a basis for its third exterior power. Okay, so I'm doing what? Suppose that we have E1 up to E5, a basis for V, then the dual basis for V star will be E1, E2, E3, E4, E5. Okay, that's the basis, the dual basis for in V star. Now, what is the basis for this, for the third exterior power? Well, we need to pick 3 vectors from here and find their wedge product such that the sequence is increasing. So you'll have something like this: E1, so 3 vectors, and the exponents must be increasing. E2, E3, E1, wedge E2, E4, E1, wedge E2, E5, right? Wedge E5, then E1. E1, wedge E3, wedge E5, right? E1, wedge E4, wedge E5. We finish with E1 on the first position. Then E2, wedge E3, wedge E4. Then this E2, wedge E3, wedge E5. Then we finished, no, E2, wedge E4, wedge E5. We finish with E2, then E3, and the only increasing sequence here is 3, 4, 5, something like that. Okay, so this will be a basis for the third exterior power of V star. Now, what's the dimension of this space? The dimension of this space will be n, which is 5, choose 3. Well, this is 10, right? And now let's count it: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, we didn't forget anything. Okay, so we do have, we are able to write basis for this exterior powers, and they are defined using they are given using the wedge product. Which means what? Which means that if you have omega alternating K form on V star, then this omega can be written in a unique way, right, as a linear combination of elements of the basis. So it will be of the form some AI1, some coefficients here, AIK, these are smooth functions, EI1, wedge EI2, wedge EIK, where this is an increasing, strictly increasing sequence, E1 smaller than E2, I2 smaller than IK, okay? All right, now a remark here is that if K is odd, K is an odd number, then, and omega is an alternating K form on V star, then omega, wedge omega, will be 0. So this returns 0, which So which product returns 0 when applied on the same forms? This is pretty clear. This comes from, you see, from the fact that the wedge product is, as we said, graded commutative. So look at this, the second property here. So omega, which omega will be -1 to k squared, omega, wedge omega, but k being odd, this will be a negative, so we'll have omega, wedge omega equals minus omega, wedge omega, which will turn into omega if wedge omega equals 0. Right, now we have this. So we did this, then this. Okay, now we are going to define the exterior algebra of V star to be the direct sum of the exterior products of V star. So this, you have something like notation like this, and then we are going to extend the wedge product on this on the exterior algebra. So I'm going to maybe okay, so maybe write this on a white paper so you see it. Okay, so we have something like this. So exterior algebra of V star, this is denoted by something like this, and that's the direct sum of all these k exterior powers. And then we take alpha and beta here, so two elements of the exterior algebra, two forms here, and well, this means what? This means that so alpha belonging to this set means that alpha will be of the form alpha I1 plus alpha I2, a finite sum, plus alpha IM, a finite sum such that every alpha here is in its corresponding exterior power. Something like this. And now, if I want to, we are going to define, for two forms like this, we are going to define their wedge product. So we extend the wedge product on this exterior algebra. So by definition, this will be something like this, gamma 0. So this is a K, so say this is a K form. And this one is a, let's say, L form. Then this will be gamma 0 plus gamma 1 plus gamma K plus L, where gamma S is defined to be the sigma of alpha I wedge beta J, where I plus J is S. So you combine them like this together. For instance, let me, again, a very simple example. Let's take alpha to be of the form alpha 0 plus alpha 1, and beta to be beta 0 plus beta 1 plus beta 2, okay? So this means what? This means that alpha 0 and beta 0 are in this space, which remember was supposed to be R. Alpha 1 and beta 1 are 1 forms, which was precisely the algebraic dual, and beta 2 is a 2 form. Okay, so how do we compute the wedge product between alpha and beta? Well, this will be some gamma 0. So I'm going up until k plus L, which means 3 in our case, 1 plus 2. So gamma 0 plus gamma 1 plus gamma 2 plus gamma 3. Now what is gamma 0? I'm taking all the combinations, all the edges, the wedge product between alpha I and beta j, where I plus j is my S, in my case 0. So you only have alpha 0, wedge beta 0. These are real numbers, so this is simply a real number, right? The product of numbers. Then what will be, so this is in this space, right? Now, what will be gamma 1? The wedge product of alpha I and beta j, where I plus j is 1. So you'll have either alpha 0 wedge beta 1 or alpha 1 wedge beta 0. Now, again, this is a number, which product number and the form means just the product. So algebraic dual, right? Then what is gamma 2? you'll have all the combinations for which I plus j is 2. So this means 0 plus 2, 1 plus 1, and 2 plus 0. So you'll have alpha 0 wedge, which means normal product beta 2, plus alpha 1 wedge beta 1, plus alpha 2 beta 0, which is a number. So it's something like this. This is the 2 form. And finally, gamma 3, all combinations for which the sum is 3. So you have 0 and 3. Then you have alpha 1 wedge beta 2. You have alpha 2 wedge beta 1. And you have alpha 3 wedge beta 0, which again is a number. So this will be a 3 form. Right? So I think it's clear now how we find the wedge product addict. Okay. Now, once we are here, we are going to we'll see that every linear map between vector spaces will determine a pullback, right? So suppose that V and W are vector spaces, and then we have a map between the vector spaces, a linear map, and we are going to define the pullback induced by A. And this is the map that we define by A star, right? Which is defined on the exterior algebra of W star. We have a plus here and the wedge as we define it, right? With values in the exterior algebra of this is W star as a pullback. So you switch you flip them with a plus and wedge product and define like that. So you see A star, so acts here, but this is a direct sum of kth exterior products. So when you see it as defined on this space, on the k exterior power of W star, with values in the k exterior power of V star, then a form here, an alternating k form, will go into something that we denote by something like this, and then we define it as, so must be here, right? So it applies on k vectors here, and this is by definition omega applied on A of V1, A of V2, up to A of Vk. Okay, so this is an element of W. You see, A runs from, so this is correctly defined. All right, so you see, this is the pullback induced by A, and we are going to see why I need it defined in a while. So we are going to apply all this on a particular vector space that we already talked about, just a little bit of a patience. So we did all this. Okay, now so this is the pullback induced by A, and A star, the pullback, is a homomorphism of algebras. That means that when you apply it on the wedge product of alpha and beta, this is the wedge product of the images. Okay. All right. Now, before going and talking about the cotangent bundle, let me give you one more remark here. Suppose that you have V, an n-dimensional vector space. Okay, and so again with a basis E1, En, a basis here, and then you take the dual, again n-dimensional, and the basis of the dual, as we denoted by until now, is given by something like this. And then let's look at the nth exterior power of V star. So n being the dimension of the space, the nth exterior power. Now this is called the top exterior power. The top exterior power of V star. Well, what will be the dimension of this space? The dimension of this top exterior power. So remember, when you have a k here, then the dimension is n choose k. So here you have n, so this is n choose n, which is 1. So this space is one-dimensional, which means that every form, every n alternating form on an n-dimensional vector space V star can be written as, well, as linear combination of the basis. How many elements in the basis? One element in the basis. What is exactly the basis? Do you remember? Which product of these vectors in which the indices, the exponents are increasing? So you have one single vector in the basis here. E1, wedge E2, wedge En. So every n alternating n form on V star will be f some function E1, wedge E2, wedge En. Okay, we are going to need this. Okay. All right. Now, any question here? Any question? Questions?
في أسئلة متدربين؟ في أسئلة ممكن كتابة في الشات. No answer, Doctor.
All right. Okay. Very well. So we are going to apply all these algebraic things on the particular case in which V is the tangent space as a point to a manifold. Remember, we talked yesterday about this. And so we are going to also need the V star, which means the dual, the algebraic dual of the tangent space at a point to a manifold, and this will be the so-called cotangent space at a point to a manifold. Right, so a few words about the cotangent space. Let's suppose that you have a manifold, and then do you remember what the tangent space at a point to a manifold is? The set of all tangent vectors. It has a structure of vector space. The dimension of this space is the same as the dimension of the manifold. So let's say M, and then so it's a vector space. As for any we know a basis for this space. So as for any vector space, we can build up the algebraic dual of the space, which is again the space of all linear maps, real valued linear maps defined on this space. Now, this is called the cotangent vector when the vector space is a tangent space. So the space is the space of the cotangent space at a point to manifold, and the elements are called the cotangent vectors. So let me write this because we are going to use it heavily in what follows. So the cotangent space of M, a manifold, back to our manifolds. For every M, if we take a point P of M, we can build the tangent space at the point P to the manifold, and then we build its algebraic dual. So this is simply the set containing all maps defined on TPM with real values which are linear. And this is called the cotangent space, the cotangent space at P to the manifold M. A vector here is called a cotangent vector. So an element here, it's a cotangent vector. And we can build up, as we've done for the tangent spaces, we can build up the cotangent bundle. So we have the cotangent bundle of M, which is the disjoint union. Is defined similar with what you've seen last time for the tangent bundle. So the cotangent bundle, what is an element here? So this means, so you take every cotangent vector at P together with the origin here, right? Where P, this is just to show that we have a disjoint union, and so the P is in M, and WP is a linear map defined on the tangent space. All right, so what is a cotangent vector? That's simply a linear map defined on the tangent space with real at a point to manifold, at the point to the manifold with real values. A very immediate example of a cotangent vector is the differential of a function. So let's suppose that you have a function, a smooth function defined. So do you remember that this means that the function is defined on M with real values and is smooth? And let's suppose that P is a point of M, right? If you have a smooth function here, we can always find the differential of this function. So the differential of f at P, this will be what? This will be defined on TPM with values in the tangent space at f of P to R, but this is the same as R, right? We talked yesterday about. So you see, this is a linear map, the differential. So we have a linear map defined on TPM with values in R. So this guy belongs here. This guy belongs here. So it's a cotangent vector. It's a cotangent vector at the point P to the manifold M. All right. So that's the an example for the for cotangent vector. And then remember, let's think a little bit of all its basis theory and everything. So suppose again that you have a manifold. Right. So remember, our space V is TPM. So V star will be TPM star. These are tangent vectors. These are linear maps defined on the tangent space with real values. Now, suppose that you have a point P here, and then it's a manifold, so we can take a chart about this. Let's put coordinates, let's call them x1, xm, the coordinates on the chart. Now, you know that we can build up a basis for TPM, right? So basis for TPM, for tangent space at the point P to M, right? It's a basis that depends on this local chart. So this is given by, if you remember, we saw them yesterday, partial over partial x1 at P up to partial xm at P. So this is a basis for TPM. And then we have always a dual basis, which will be a basis for the dual space. So we have it's dual basis, right? So we are going to denote it. So it's dual to B, to the basis for TPM. So we are going to denote this by something like this. These are the differentials of the coordinate functions, right? So P up to differential of x m at P. Okay. So dual simply means that, you know, probably from linear algebra, means something like this, that the differential of x I at P computed at the differential of partial over partial xj at P. This is the Kronecker symbol, right? So this is like this, partial xi over partial xj, right? At P, and this is the Kronecker symbol. That's 1 when I and j are equal, and 0 when I and j are distinct. Okay, so we have a basis. We have a basis for the cotangent space at the point at a point to the manifold. Very well. And now we are going to apply all what you've seen at the beginning of the lecture. We are going to apply it to the cotangent space. Okay, so this is the basis for TPM. Okay, it extends to a frame, so like a basis for the cotangent bundle. So let's come here and let's see. So do you remember we talked when we started? We talk about the k alternating forms on a vectors on a dual of a vector space, and we build up the k exterior power, the set of all these alternating forms. So this is what we are going to do for TPN star. So we say that we call the k exterior power of the cotangent space at P, right, to be this lambda k TPN star, and the collection of all these vector spaces will be called, like a disjoint union, will be called the k exterior power of the cotangent bundle. Now we are going to apply the previous theory on this on this vector space, right? And so you always start with the manifold. You take a point on the manifold, and then you take a chart about that point. This chart will give you coordinates. A chart is like a system of coordinates. So suppose that the coordinates, as we said, are given by x1 up to xm, right? And then they will induce they will induce a basis on TPM star, which will induce a basis on this kth exterior power of TPM star. Do you remember this is the wedge product of the elements of the basis, where the indices are taken increasingly, and you take wedge products of k such terms from the basis, right? So again, I'm going to write it. Maybe it's easier to understand. So we take the set of the kth, so the kth exterior power of TPM star. Do you remember what this means? This means that you'll have maps defined on the Cartesian product TPM by TPM k times with real values, which are linear, multilinear, linear in every variable, and alternating. Okay, and then, so what is an element? What is an element here? It's a map applied on k tangent vectors. And then suppose that we take u phi, a chart about p, p being a point of M. So again, I suppose that M is a manifold with dimension M. So suppose that this chart has coordinates x1, xm, right? Then what will be a basis for this kth exterior power of TPM star? Well, it's given by what? It's given by elements of the form. So do you remember what is the basis for TPM star? Is the basis for that. So we take wedge product of k vectors here, right? Where the exponents are increasing. So you'll have d. This is the differential of coordinate function, as I said, wedge dxik at p, right? Where 1 is less than or equal to I1, less than I2, less than Ik, less than or equal to m, right? So n choose k elements in the basis. So this means that an element here, right? So an element here will be of the form. So if this map is here, it's a map, right? So the k, this alternating k form on TPM star will be of the form, can be written uniquely as sigma, right, of some coefficients here. We have some coefficients. These are functions, smooth functions, dxi1 wedge differential of xik at p, right, where this sequence is increasing. Okay, something like that. So it's the theory that we've seen at the beginning, applied on this particular vector space. All right. So now we know what the kth exterior power of TPM star is, and let's go and see. Okay. So this is what we talked about. Let's see what is a differential form on M. This is our goal, because we are going to integrate forms on manifolds, right? So first we are going to define a differential form of degree k to be a section of this kth exterior power of TPM star. If you remember, a section is a map. I'm going to remind you, you heard the word section. We heard the word section yesterday when we were talking about vector fields. So a section of this kth exterior product of TPM star is simply a map, contains maps from M into this space, right? So let me write it down maybe properly. So we build up this. Okay, so we say that a k form on M, or a differential form of degree okay, is a section of this space. That is, so we are going to denote them by something like this. This is the space of differential forms of degree k. The sections are denoted by gamma, if you remember from yesterday, so something like that. And this simply means that an element here is a map, okay, is a map running from M, from the manifold into the space, such that every point P here on M is taken into omega P, which will be in this space here, so associated to the cotangent space at P to the manifold M. So this will be what? So this being here, living here, this means that it's simply a linear map, linear and alternating map, right? This is what we started with, okay, linear and alternating. So it's something like that. Now, if k is equal to 0, then omega 0 of M is the set of smooth functions of M, okay, something like that. All right. Now, the wedge product can be defined, so we take all the, okay, so we denote by something like this, the direct sum, so all together, like you've seen previously on the other product, so it's something like that, direct sum of the spaces, which means that every form, so differential form, will be a differential form of degree 0 plus 1 in omega 1 plus up to something like that. Every omega here belongs to the corresponding space, right, of differential form. So it will be a differential form of degree I on M. Okay, and now we can define the wedge product, right? Extending the wedge product. Yeah. Okay. On this. This will be an algebra. We can define an edge product, and the properties for the wedge product are the same as you've seen before. So you see, for instance, it's graded commutative, right? So that -1 to KL appears there. Then again, forget about the interior product. Just remember this graded commutative thing. I'm going to take an example to tell you how we find the wedge product of two forms like that, right? So we can see it. So suppose that I'm going to take an example here. I'm going to take alpha to be a 1 form on R3. So a 1 form, so when you look at gamma omega 1, right? A 1 form. So this will have a basis, right? So you'll have something like this, x dx plus something dy plus y dz, right? Then, so this is a form here. Then let's take beta 2 form, so something like this. All right, so you will have what? The basis will be given by wedge product, so for R3. So for omega 2, you will have wedge product of two differentials, right? To get base. So you'll have increasing. So imagine that x less than y less than z, right? This is the order, alphabetical order. So you will need something something with dy dz. So let's say y dy wedge dz plus x dx wedge dz plus, I'm going to take a dx wedge dy. Okay, so this is a 2 form on R cube. So you see it's a linear combination of this wedge product of 2 forms, right? So let's see what is alpha wedge beta. Okay, so each by each, right? So this by this. So you will have xy dx wedge dy wedge dz plus this by this. So I have x squared dx wedge dz, right? Then I'm having this by this. So I have plus x dx wedge dy plus, I'm moving here. So I'm taking with this, wedge product with this, so I have y, dy, wedge, dz, plus, I'm moving here, so dy, wedge this, so I have an x, dy, wedge, dx, y, wedge, dz, plus, I'm moving to this one, y, wedge, dx, wedge, dy, plus, then I move to y, dz, so I have an y squared, dz, wedge, dy, wedge, dz, plus yx, I'm here, dz, wedge, dx, wedge, dz, plus, and I move here, I have a y, dz, wedge, dx, wedge, dy. Okay, now let's reduce a little bit here. You remember that the wedge product of a form by itself, right? This is an odd number, it's 0. So this is 0, then this is 0, then I have dy, wedge, dy, that's 0, dy, wedge, dy, that's 0, dz, wedge, dz, that's 0, dz, wedge, dz is 0, and that's all right. So let's see, I still have this one. So I have x, y, dx, y, wedge, dy, wedge, dz. Then I have this one, plus x, dy, wedge, dx, wedge, dz. And then I have this one, right? Plus y, dz, wedge, dx, wedge, dy. Now, we haven't finished. You see, this is so this one, it's a 3 form, right? A 1 form, wedge 2 form. This will be a 3 form. Now, what's the basis for omega 3? You have one single element there, right? Dimension 1. The x, wedge, dy, wedge, dz, increasing, you arrange them increasing. So you need to write all of them, right, like this. So x, y, this is already the x, wedge, dy, wedge, dz. I'm coming here, okay, at this one. I need the x, wedge, dy, wedge, dz. So I'm flipping these two. When you flip them, you get minus there. So it's minus x, dx, wedge, dy, wedge, dz. Right, and then I'm looking here. I'm flipping dx with dz. I get a minus, and then dz will be on the second position. So I'm moving it here. So another minus. So it will be plus y dx wedge dy wedge dz. Right. So you can write them as this as xy minus x plus y dx wedge dy wedge dz. Right. So it's clear, I guess, how we find the wedge product of two forms. Okay, any question here? Questions?
في أسئلة حتى لو تبغوا المايك ممكن فتحه. اكتبوا في الشات فضلا إذا في سؤال.
No, we are good?
نعم, they don't write anything.
Very well. So again, suppose that just to make sure that we keep going, if we are on R3, right? If we are on R3, suppose the coordinates are x, y, and z. What are the 0 forms? Forms on R3. Well, these are the smooth functions, remember? So smooth functions defined on R cube. What are the 1 forms on R cube? So everything is on R cube here, right? Well, what is a basis here is given by dx, differential of x, differential of y, differential of z, right? So you have linear combination of something like this. So you will have f dx plus g dy plus some h dz, where this f, g, and h are functions, smooth functions on R3. What are the 2 forms? What are the 2? What is the basis for the space of 2 forms? So wedge product of 2 differentials increasing. So dx dy, dx dz, and dy dz, right? Wedge dz. So the 2 forms will be of the form f dx wedge dy plus g dx wedge dz plus h dy wedge dz, where again f, g, and h are functions, smooth functions on R3. And finally, what are the three forms? Well, the basis only has one element, this wedge product, so you'll have three forms of the form, some function, some smooth function, dx, wedge dy, wedge dz, okay? F is a smooth function, right? So something like this. So this is important, right? We are going to use them, okay? Now, we know what a form is, okay, on a manifold. This, as we've seen until now, the differential forms can be pulled back. So we can define the pullback along a smooth map of a differential form, and it's defined here. You see, goes from let me write it. Let me write this pullback down. So suppose that you have f, a smooth function between manifolds, okay, and then so smooth, and then the pullback. So we pulled it back. The pullback along f is defined by f star going on the space of k forms, k different forms on n. So pull it back into k differential forms of m, in which a k form goes into something like this, where so this lies here. So this f star omega will be a map. It's a section of the kth exterior power, right, of TP and star, something like this. So this will be, so let's say point P goes into f star omega at P, right, which is by definition, so that's the definition, the differential of P, the pullback of the differential, you see, at omega of f of P. Okay, this simply means, so this means that you have something like this, f star omega at P, so you apply it on W1, on some vectors V1, Vk, right? And this will be what? This will be omega at f of P applied on the differential of f at P of V1, right? You go the pullback of the differential of f at P of Vk, something like that. Okay, and our immediate properties from pullback, and then we go and compute some examples in a short moment. So, right, it's easier to understand. So if the pullback of the wedge product is the wedge product of the pullbacks, the pullback is linear, so A alpha plus B beta is A F star of alpha plus B F star of beta, and the pullback of the composite is the composite of the pullback, but the other way around. Okay, so properties of the pullback. Okay, let me here. All right, so what we have here. Remember this one. We'll see how we are going to compute it. Now it's time to go and define something which is called the exterior derivative. The exterior derivative on a manifold. So suppose that you have a manifold, and then you take these spaces of k forms, and we can prove that there exists a unique map, which we call D, which we denote by D, and we call the exterior derivative, taking a k form into a k plus 1 form, satisfying the following properties. D of a 0 form is just a differential. Then D composite by D is 0 for every form, and then it's a graded derivation. So the exterior derivative on the wedge product of alpha and beta is the derivative of alpha wedge beta plus minus 1 to the k being, you see, that grade of the force we are on the domain, alpha wedge product with d beta. Okay, and very important is that this exterior derivative commutes with the pullback. You see, the exterior derivative of the pullback of f at alpha is the pullback of the exterior derivative for alpha. So we are going to use this. Sorry, and let me. Yes, so this is called the exterior derivative. Let me write it here so we see it. Okay, so we define like this. We define d from the k forms into the k plus 1 forms on a manifold. So k greater than or equal to 0. And we have that exterior derivative on alpha wedge beta. This is d alpha wedge beta plus minus 1 to the power k alpha wedge d beta. Okay, graded derivation, we say it. It isn't the exterior derivative commutes with the pullback. So this is a pullback of d alpha for every alpha here. Okay, something like that. So f goes from n to n, right? So this will be an n here, something like that. Okay, and now suppose that you have a k form. Suppose that you have a k form on n, right? We saw, right, a little bit of time before that this is a linear combination of something like this, right? dx I1 wedge dx ik. You can have some coefficients here, a I1 ik, which are smooth functions on U. So let's say this is an open neighborhood bounded point, and this sequence is increasing. So something like this. So when we apply d on a form, so there's a k form, when you apply d, the exterior derivative of omega, this is what? This is d of the sum, all right? And then this will be sigma of d applied on a I1 ik wedge dx I1 wedge dx ik. Okay, remember that these are functions, smooth functions. Let's take some examples here, okay? Let me see, I have some examples, I guess, here on the, oh no. All right, let's look at example 3, for instance. Okay, let's look at this example 3. So let's compute the pullback. And then, yeah, let's start with 3. We are not ready to do 1 and 2, but we will. All right, so example 3 says this. Suppose that you have a function f from r squared into r cubed given by f of u and v equals u, v, and u squared minus v squared. And let's take the following two form on r cube. So it's a two form, it's y dx wedge dz plus x dy wedge dz. Something like this. And we want to find the pullback. So the pullback, okay, let's go and compute f star omega, the pullback along this. So this is what? This is f star of y dx wedge dz plus x dy wedge dz, right? I'm just replacing it here. And this will be what? This will be, so it's y, right? Y, but what is y? Y is v, so v. And then, okay, let me make you understand a little bit better, maybe here. So, oops. So this will be what? This will be f star of y, f star of dx wedge dz, okay? Plus f star of x f star dy wedge dz. Okay, you remember we apply f star and f of alpha wedge beta. This is f star of alpha wedge f star of beta. Now, because y is a function, not a, so it's a zero form, this product is the classical product, right? We had this, we explained it before when we took the examples of wedge products, Now, this is what? So f star of y, this will be, so f star of y is the pullback of a function. This is y composed to f, is the y of f. The y of f is v. This is v. Now here we apply this, right? So this is f star of the differential of x, wedge f star of dz. Plus, now this is x of f, right? X of f, so is the x of the function. This is the u times f star dy wedge f star of dz, okay? Which will be equal to v. Now f star of d of dx, this is remember that the f star commutes with d, we wrote it somewhere, yes, something like this. So this will be d of f star of x, wedge, again, f star and d commutes, d of f star of z, plus u, now again, f star and d commutes, d of f star of y, wedge, d of f star of z, okay? And this will be v. Now d of what? What is f star of f? This is x of f. So this is the x of f, which is u, the differential of u. Wedge, I'm looking here. This is the differential of z, which is u squared minus v squared, plus u. This is the differential of y, which is v, dv, wedge, d, and f star of z, this is z is the u squared minus v squared. Okay, something like that. So we have v du wedge. Now, what is this differential? The differential of u squared minus v squared, this is plus u dv wedge, again 2u du minus 2v dv, okay, which will be v du, okay, so let's multiply here. So this is 2uv du wedge du minus 2v squared du wedge dv. I'm coming here, plus 2u squared dv wedge du minus 2uv dv wedge dv. Okay, now remember that this is 0. Du wedge du, vectors that coincide, this is 0. Now this one here, it's minus du wedge dv, right? So we'll get this one, which is minus 2v squared du wedge dv minus 2u squared du wedge dv, or you can write it as negative 2u squared plus v squared du wedge dv, right? So this is how we evaluate the pullback of a longer function. So let me see. Oh, no, sorry. Any question on this? I'm going to, you know what happened. I'm going to take another example. Any question here? I'm going to take example 4 also. Okay, exercise 4.
إذا في أسئلة اكتبوا في الشات أو ممكن فتح المايك. You don't write any question.
Okay, then I'm going to look at example 4 also, you know, before the break. And so they have another example of how we go with the pullback. So we can, so I can at least, you know, be think hopefully they understand. So let's take h from R into S1, defined by h of t equals cosine of t, sine of t. And then we take the following one form on S1. So it's minus y dx plus x dy. So we take, this is a one form on S1. And we want to find the pullback along h. So the pullback of omega along h. So h star of omega. This is h star minus y dx plus x dy, which will be, so this is negative y, which means minus sine of t, times h star of dx plus x, which is cosine of t, h star of dy. Now h star in d commute, so that's minus s of t, d of h of x, plus cosine of t, d of h of y. So that's minus sine of t, differential of h, this is, it's a star here, so I commit with star. This is x of h, so that's the differential of cosine of t, plus cosine of t, the differential of sine of t. Now this is minus sine of t dt, and this is cosine of t dt, right? So this will be sine squared of t dt plus cosine squared of t dt. Sine squared plus cosine squared of t is 1, so pullback is dt. Okay, very, very simple here. All right, so hopefully we do know how to find pullbacks. All right, now let me explain you something also before the break, just because I have time. And let's look a little bit at differential one forms. Okay, so just to remember before the break, just to make some sort of revision before the break. So suppose that M is a smooth manifold. Okay, and then P is a point of M. We build up TPM star. Okay, so what is a one? So remember, this means functions defined on TPM with values in R which are linear. Okay, then what is a one form on the manifold M? Something which belongs here, right, in omega 1 of M. Well, it's simply a map which runs from M onto P star. So I'm going to take the cotangent bundle. So this, remember, is this joint union here of the cotangent spaces. Every point P goes into omega P, which is here. So something like this. Okay. Now let's look, for instance, at dxi that we keep talking about, right? So if you see them as functions running like that, these are one forms when P, it's taken into dxi P, right? And this will be a cotangent vector at P to M. So this means that this differential of coordinate functions is P will run from TPM into R. So they will apply on a tangent vector, you see? So you have that dxip on a tangent vector xp tangent. So this will be what? dxip. Now, if you remember, a tangent vector can be written as a linear, at the point P to the manifold M can be written as a linear combination of the elements of the basis. So the bases here are vectors of the form partial over partial xj at P, right? So we take j running from 1 to M, let's say here, and then you have some functions here, right? Some coefficients which are functions of P. And this is simply, this is the sum of xj at P times dxip applied on partial xj at P. But do you remember, this is the Kronecker symbol. So everything is 0 except when I is equal to j. So this is simply xi of P, the ith component of the vector xp. Okay, so in fact, what we mean by this is that if M is smooth, defined from M into R, so smooth function, then the differential is a one form. So this one is a one form, can be seen as a one form on M, right? Every P goes into the differential of F at P, which we saw is a cotangent vector at P. So this means that the differential is a linear map from TPM into R. Okay, and now if we take basis here, so if about the point P you take a chart, so you'll have coordinates x1, xm about the point P. Okay, then what is the basis for the cotangent space TPM star? Well, this is given by dx1p, dxnp, right? The dual basis here. So every one form, remember I'm talking about one forms here, every one form, I did write somewhere, yes, every one form will be written as some sigma of ai, dxi, right, can be written formally like that, where these ai are smooth functions on the domain of the chart. Okay, so in particular, when this one form is the differential of the function, then this is sigma partial derivatives of f with partial derivatives of f with respect to xi, dxi, right? So we know this. All right, something like that. Okay.
Okay, Doctor.
All right. So I think I'm going to take the break now.
Yes. إن شاء الله 6:40 we come بإذن الله.
Okay. All right.
Thank you.
Bye.
Bye. السلام عليكم ورحمة الله وبركاته. نكمل الجزء الثاني من دورة هندسة ريمان مع الدكتورة ليانا توبان، وتذكير راح نرسل رابط الحضور إن شاء الله الساعة 7:30 بإذن الله. ويلكم دكتور ليانا.
Sorry, I forgot to unmute. Should I start? Thank you.
Thank you. Start, yes.
All right, very well. So one more thing before moving on to integration of manifolds. Suppose that you have a K-form on a manifold M, and this is called, so omega is called closed if its exterior derivative is 0. And omega is called exact, an exact form, if omega is the exterior derivative of f, where f is some k-1 form on M. Okay, so exact form and closed forms. And I'm going to take an example here so we can calculate the exterior derivative. So let's look at omega, the following form, 1 over x squared plus y squared times negative y dx plus x dy. This is the one form on r squared minus 0, 0. And we are going to show that omega is closed. To show that it's closed, we just compute its exterior derivative. So we want to see what is the exterior derivative of omega. And so this will be the exterior derivative of negative y over x squared plus y squared dx plus x over x squared plus y squared dy. Okay, and then so this will be d negative y over x squared plus y squared wedge dx plus d x over x squared plus y squared wedge dy. Okay, now this will be something like this, the partial derivative of negative y over x squared plus y squared with respect to x dx plus the partial derivative of negative y over x squared plus y squared with respect to y dy, everything wedge dx, so this first bracket is this, and then plus, now I'm writing this, that's partial x over x squared plus y squared with respect to x dx plus partial derivative of x over x squared plus y squared with respect to y dy and wedge dy. Okay, so when we compute here, okay, well, some partial derivatives here. So this one with respect to x, this will be so with respect to x, right? I have a negative y over x squared plus y squared squared. I have a negative with respect to x, right? Something like that. Derivative dx. I hope I'm not making mistakes here. So with respect to x, so I'm here, right? With respect to x, I have a negative minus 2 minus yes, that's correct. Dx, and then I have plus the derivative with respect to y. So I have a negative x squared plus y squared minus y, the derivative with respect to y over x squared plus y squared squared, right? Dy wedge dx, and then plus with respect to x, so that's x squared plus y squared minus x times 2x over x squared plus y squared squared dx plus with respect to y, so I have an x negative, then I have over x squared plus y squared squared, and the derivative with respect to y, that's 2y, right? Over and dy wedge dx. Okay, now whatever, so when we multiply here, this, I have a dx wedge dx, so cancels. So I only have this, so I have minus x squared minus y squared. That's a plus here, right? Plus 2y squared over x squared plus y squared dy wedge dx. And then this is dy, huh? This is dy, so plus this one, so I have x squared plus y squared minus 2x squared over x squared plus y squared squared dx wedge dy, and then dy wedge dy will be 0, okay? So here we'll have a y squared minus x squared over x squared plus y squared dy wedge dx plus, and here we'll have a y squared minus x squared over x squared plus y squared dx wedge dy. And now this is minus dx wedge dy, so this one will take a minus, it's minus x squared plus y squared, and I'm looking here, plus y squared minus x squared over x squared plus y squared squared dx wedge dy. This is 0, so 0. So you see the exterior derivative of this form is 0. So the form is wrong. So the exterior derivative of omega is 0. So this is closed. Okay. All right. Now finally, let's move to integration on manifolds. And we are going to start by defining the volume. The volume of a subset of Rn, and this is simply the integral over A over the domain over the subset dx1 dxn. Probably you know already this, provided the integral exists. And now if we take an n form on Rn, right? And again, this means that so the space of n forms on Rn, which is of dimension n, is so Rn has dimension n. The space of n form is of dimension n choose n, which is 1. So any n form will be something like this: a function, some coefficient, which is a smooth function, dx1 wedge up to dxn. So we can identify the n forms with the functions, the coefficients there, and we are going to define the integral of such a form, of an n form over A, right, where A is a subset of a subset of Rn, to be simply integral of f of x dx1 dxn, right? So I'm taking here an example. I'm going to write it like that. So again, we said that the volume of some set, the volume of a set is simply integral over the set of dx1 dxn, right? And then every n form on Rn is of the form, can be written as fx, f of x dx1 wedge dxn, right? We saw this at the beginning of the class, and we define integral over A of omega of the form, right, which is integral of f of x dx1 wedge dxn. We define it to be integral over A of f of x dx1 dxn, right? So for instance, if we take the set A to be 0, 1 times 0, 2, that's a subset of R squared, right? A rectangle in R squared, and then we take a 2 form here on R squared, so this will be, for instance, xy dx wedge dy. Then what will be integral over A of omega? This is integral over A of xy dx dy, right? So this can be split at 0, 1 x dx, 0, 2 y dy, and whatever this is, okay? Right, so now let's come here, back to my paper, okay. So, of course, the order of the coordinates is, as we've done, as we've seen so far, important. So if you switch 2 of them, then you will get a minus there. So as I say here, this omega is f of x dx2 wedge d1, then you flip dx1 wedge d2, and you get a minus there. Okay, I'm going to skip this diffeomorphism issues, and we are going to see that in order to integrate over a manifold, the manifold must be oriented. We had yesterday like 10 minutes talk about what oriented means. So just remember that, for instance, the sphere is orientable, the Euclidean spaces are orientable, and so on. I gave you an example of a non-orientable space. This is the Möbius strip. There is another one which is called the bottle of Klein, if you know it. So weird surfaces in R3. So anyway, the manifold must be oriented, and on a manifold, over a manifold of dimension n, we can only integrate m forms, and those m forms must have compact support. Now, did I explain here what is? So compact support. So compact support simply means that the set of the closure of the set is compact. So the closure of the set where the function is defined is compact. Okay, so an example for it, think of the tangent of pi x over 2, right? So the support is negative 1, 1, so open. So when you define it on the open interval negative 1, 1, the closure will not be compact, right? So you just remove the 0 there because of tangent of pi x over 2. So anyway, we denote by we need the forms to have compact support. And now suppose that you have an oriented manifold, and a class giving the orientation if you remember from the day before yesterday, when you write down those translation maps from a chart to another, those phi beta times phi alpha inverse, and you write down the Jacobi matrix of all these things, then when you compute the determinant, that determinant might be positive or negative. Now, if the determinant is positive, then the manifold is oriented, right? So we have an atlas all giving the orientation. We can define an orientation on the manifold via its atlas, and then we take all the forms, all the K forms having compact support on N, and in order to define the integral of form, we are going to use the pullback. So remember that when you have a chart, then this map phi is a diffeomorphism. So it makes sense to talk. It makes sense to talk about the inverse. So you take the inverse of this map, and then you take the pullback of this inverse, and we define the integral over u being the domain of a chart of omega of a form to be the integral over phi of u of the pullback along phi inverse. Okay, so I'm going to write down this, so I remind you a little bit all these things. The day before yesterday was a long time ago. So suppose that you have M manifold, right? You take U phi, a chart here, which means that phi from U into phi of U is a diffeomorphism, if you remember this. And this is a diffeomorphism onto an open subset, say this is M-dimensional, into an open subset of Rm. So it makes sense to talk about phi inverse, right? Which is defined now on Rm into a subset of M, into U, an open subset of. Now we apply the pullback. So every function can determine a pullback along. We can find the pullback along this function. If you remember, it's something like this. We pull back the forms from forms on U into forms of phi of U. This is what we are doing. So we go with support compact here from M forms on U into M forms of phi of U, the pullback support compact. So this omega, a form on U, will get taken into a phi inverse star of omega. Okay, so this is, you see, this one here, this is a smooth M form here. So but remember again, phi of U is a subset of Rn. So this is a smooth M form on R of M, on an open subset of R of M with compact support. So we define the integral over U. So again, U is a subset of the manifold, right? But we define it the integral of omega here. We define it via phi of U, right? Integral on phi of U of phi inverse the pullback of omega. And now we can prove. So again, a form on a subset of Rn. So again, we can prove that this definition is independent on the choice of the representer. So if we change the charts, then the integral will be the same. So if you take another chart, the same thing, and you compute psi inverse, pullback star of omega on psi of U, then you will get the same thing. So the definition is correct. Also, the integral defined like this will be linear. So when you evaluate the integral of A omega plus B tau on some U, right? Omega and tau being forms, this will be A integral of U plus B integral over U of tau. Okay, so now let's see how we can. So in order to evaluate the integral over a manifold of a form, we are going to evaluate integrals over an open subset of Rm of Euclidean space of forms, right? So let's see what we can do this, right? So let's try to understand. So we are going to do what we are doing, on when we integrate functions, real valued functions with one variable, we are going to parameterize these domains. And now, maybe I will show you this here. All right, so All right, so suppose that you have an oriented manifold and a subset of M, and then a subset of Rm. I have a small picture here. I will make a larger one on a white page. A compact domain of integration. Now, a compact domain of integration means that it's bounded, and its boundary is of measure 0, topological measure 0. So bounded and of measure 0. And now, if we can define a function which is smooth between D and A, such that A is the image of D, and such that the restriction of F to the interior of this domain of D and of its image is a diffeomorphism that preserves the orientation. Now, these are technical details. A diffeomorphism will be orientation preserving when the determinant of its Jacobi matrix is not 0. So when the Jacobi matrix is not singular. So something like this. So if we can define such a diffeomorphism, then A, the set of M, the subset of M, is called the parameterized set of M, and that function is called the parameterization. So we simply parameterize a subset of a manifold via a subset of Rn, right? Which is where we know how to work with. I'm going to draw this thing here so we can see. So what we mean is this. So you have a manifold, okay? You have a manifold here, a manifold M, and then you take a subset of M here. So we want to parameterize this. So we are trying to find a function f that takes some domain, so D of Rm. So M is the dimension of the manifold. Some domain of Rm, which must be compact and well of measure 0, boundary of measure 0. We want the interior of this domain to go into the interior here, all right, such that when you restrict the function, you get a diffeomorphism that preserves the orientation. You see, so in fact, we parameterize A. Now, this D is called the domain of integration. A is called a parameterized set of M, and F is called a parameterization. And now, once we so do you remember why we're doing this? Why are we doing this? Because we want to define integrals. We want to define integrals over domains of Rm of some forms, right? So this we are going to go from integral of A over A of omega into something here. Now, how can I do this? You see, I need to go back to Rm, so I'm pulling back so I have a form defined, an M form defined here on M, so I want to take it into a form of Rm, so I'm pulling it back. So I'm pulling it back via F star omega. So I'm going to define the integral over the domain A, right, subset of M, to be integral over the domain D. So again, this is a subset of Rm. And I have a form which is a form on Rm. So we know how to integrate forms of Rm, right? We saw here what this means. So let me take an example here, okay, to see how we integrate a form on a manifold. Okay, so let's take the sphere, the two-dimensional sphere, as a subset of R3. Remember, this is x squared plus y squared plus z squared equals 1. And then we take the following two form so remember, on a manifold of dimension m, we only integrate m forms, right? So I want to calculate integral of s squared over s squared of a form, so I need that form to be a two form. So I'm taking the following form as an example. So it's dy wedge dz, two form. Remember, dx wedge dy, dx wedge dz, and dy wedge dz. So I'm taking it like this. This, when x is not 0, dz wedge dx over d over y, y, when y is not 0, and dx wedge dy over z when z is not 0. So I'm going to evaluate this, okay? So let's use our previous idea here and the definition. So we need to so our set, what is it? Our set A is the two-dimensional sphere is 2, so I need to parameterize the sphere. So we parameterize it like that. I think everybody knows how to parameterize the sphere, right? We take the spherical coordinates, then sine of phi, cosine of theta, y is sine of phi, sine of theta, and z is cosine of phi. And then you see we parameterize S2 on the domain on the domain phi theta of r squared, such that phi runs between 0 and pi, right? Spherical coordinates, everybody knows, and theta runs between 0 and 2 pi. Okay, so and then we are going to, so this is our domain, right? Now we, of course, we are going to define our function on the domain with values on the sphere, right? So this function f that we see here as f of phi and theta. This is the one-dimensional sphere, right? That's why we don't have an r there. So f of phi and theta is, well, as we see here, x, which is sine of phi, cosine of theta, sine of phi, sine of theta, and cosine of phi. Okay, and now I'm not going to compute it, but this is an orientation preserving diffeomorphism. This preserves orientation. If you compute the Jacobi matrix, the determinant of so the Jacobi matrix will be sine of theta, of phi. And now phi is between 0 and pi, right? So this will be positive, so it's okay. All right, now we want to find the integral of over s squared of this form omega. Now this by definition, right? Is wrong here. So this by definition, this is integral over our domain D of the pullback of omega, right? Something like that. Now let's go and compute the pullback of omega, right? We had some examples of how we compute the pullback. So let's go and compute it. So I assume at the beginning that x is not 0. Okay, so I'm going to evaluate the pullback of this thing. So f star of omega, this is the pullback. So f star of, what was omega? I forgot again. What is it? dy wedge dz. dy wedge dz, right? So let's go and evaluate. So over x. So this will be what? I have a 1 over x, right? 1 over x, f star dy wedge dz, okay, which is 1 over x, f star dy wedge f star dz, f star and exterior derivative commute, so that's 1 over x, d of f star y plus d f star z, which is 1 over x, d, now f star y is y, the y of f, which is sine of phi, sine of theta, sine of phi, sine of theta, wedge, it's a wedge here, right? D of z is cosine of phi, right, for the sphere, something like that. And now let's go and evaluate. So x is 1, so x, I didn't replace x, so this is 1 over sine of phi, x is sine of phi, cosine of theta, right? So I need to write here sine of phi, cosine of theta. And now d of sine of phi, sine of theta, so the derivative of sine of phi, that's cosine of phi, d phi, right? So I forgot the sine of theta, d phi plus sine. And wedge, and here this is minus sine of phi d phi, right? So equals 1 over sine of phi cosine of theta. All right, so I have this wedge, this will be 0 because it's d phi wedge d phi. So I'm coming this and here. So I'll have what? I'll have a minus sine squared of phi cosine of theta d theta wedge d phi. Okay. I can simplify the sine. I can simplify the cosine, and I get minus sine of phi d theta wedge d phi. Remember that we arrange this increasingly. So phi was the first variable. So this is minus d phi wedge d theta. So this will be sine of phi d phi wedge d theta. Okay. So we get something like this. And now if we take you know the expression of the, let's see, if I take the expression of the form when y is not 0 and z is not 0, and I calculate the pullback, I get the same result, right? So we'll obtain the same result. So this means that this pullback is always minus, it's all sine of phi minus sine of phi, plus, it was plus, sine of phi d phi wedge d theta. Okay, so I'm going to go and replace here, right? So we'll have what? We'll have that. Okay. Sorry, wrong. Something's wrong. Can you hear me? Hello, can you hear me? Hello? Yes, all right. So
Yes,
just give me yeah, sorry. So I don't know if something's wrong again. Give me 1 second, please. Note. Okay. All right. Okay, here we are. So wrong. Something's wrong with one note. No, maybe now it works. Okay. Here. Yeah, okay, we are here. Come on. Right. Okay, so here we are. Sorry about this. So we said that f star. Oh, come on. F star Okay, is it back? Yes, F star, the pullback is, sorry, sine of phi, d phi, wedge, d theta, okay? Now, we say that the integral over S2 of omega is integral over d squared of F star omega. Now, remember, please, d squared, it's not d squared, it's d. Remember what d is, right? So contains the sets of rho phi. I'm going to write it again, but it's just easier. With phi between 0 and pi, and phi theta and theta between 0 and 2 pi. Okay, so this is the domain. So this is integral over 0 pi times 0 to pi of sine of phi d phi wedge d theta. Okay, so this is what we get. Now we know how to calculate this. This will be equal to integral 0, so 0 pi wedge times 0 to pi sine of phi d phi d theta. We drop the weight by how we defined it. Zero to 2 pi d theta, okay? Which means, so this is what this is, negative cosine of phi from 0 to pi, and this is theta 0 to pi. So that will be, so it's minus. Okay. So that's how we find, how we evaluate integrals over manifolds using parameterizations. Okay, now let me take one. What time? Yes, there is time to take one more example here. So I'm going to do this. I'm going to calculate the area of an ellipse. So find the area. Find the area of an ellipse with equation x squared over a squared plus y squared over b squared equals 1. So we know what an ellipse, right? Something like this. So I'm going to remember that the area is simply integral of over the ellipse of 1 dx wedge dy, right? We define the volume at the beginning. So we would like to see how can we, so E is the ellipse, right? This domain here with the interior. So we can parameterize the ellipse like that. We can take x equals AU and y equals to BV, right? So when you replace it here, you have a squared u squared over a squared plus b squared v squared over b squared equals 1. So u squared plus v squared equals 1, right? So the interior of what we get here is the circle, the disc, right? Circle together in the interior with radius, with center 0, 0 and radius 1. If you look here, what is dx? This is a du, right? What is dy? This is b dv. Okay, so what will be integral over the ellipse of 1 dx wedge dy? This is integral over the domain D, which is what? The domain D is given by u and v such that u squared plus v squared is less than or equal to 1, right? So over the domain D of dx, that's a du, wedge dy, that's b dv. So this is ab integral over the domain D, du, wedge dv. But this is precisely the area of a circle. Area of a circle, right? Here, this is the domain with center 0, 0 and radius 1. So this is AB times pi times r squared, which means A times B times pi. Okay, so we can calculate the area of regions in the plane like that. Very well. Finally, let's go and see, let's move on to the famous Stokes theorem, which is, so we did this, which is here. So Stokes theorem says that, so remember, on an n-dimensional manifold, we can integrate m forms, right? So Stokes theorem says the following, says that if m is an oriented manifold and you take omega on n-1 form with compact support, then integral over m of d omega will be integral over the boundary of m of omega. See, I'm going to just make a small remark here by writing it. So Stokes theorem says this, says integral over m d omega is integral over boundary of m of omega. Now, m is an m-dimensional manifold, which means that, you see, if you look here, this d omega must be an m form. So omega itself will be an n-1 form on m, compactly support. And now if m, if you remember from yesterday, we went very fast through this, is if m is a manifold with dimension m, then the boundary of m is a manifold with dimension m-1. So here, this is of dimension n-1 and omega is an n-1 form. So it makes sense, right? At least at this level of what we write here. So this is called, I'm going to write it again. It's a very important theorem. This is called the Stokes theorem. Okay. Now, as a very fast remark is that when the boundary of M is 0, so when we have a manifold with no bound, without boundary, classic manifolds, then the integral of omega is 0, right? If the boundary is empty. So if this is empty, then the integral on the boundary will be 0, which means that integral of d omega over m also will be 0, right? And then let's see, there are some corollaries here, but I will come back to this when just one of them because it's immediate and pretty easy. So let's see what happens if we apply this Stokes theorem on a segment, right? So again, integral over m of d omega equals integral over the boundary of m of omega. So let's take m to be the closed interval AB. Okay, the closed interval with the standard orientation. And let's take f to be a 0 form on AB. The 0 form means smooth functions on AB, if you remember. Right? Now, if we write it here, we'll have what? Integral on m, so the integral on the interval AB, so from A to B, right? I'm going to take here the differential of f, right? This is equal to what? Using Stokes theorem, this will be integral on the boundary of m. The boundary of the interval AB contains 2 points, A and B, of f, right? But this is what? This one will be f of B minus f of A. F, you see, it's a 0 form. So when we calculate the integrals here, this is simply a sum of values. You have some points there. Now, this f of B minus f of A simply says the f of B comes with plus. B will be positive for the orientation induced on the boundary, and A will be negative, right? This is the classical orientation. So you see what we get is the fundamental theorem of calculus, right? For a very particular case of Stokes theorem. Now, another remark here is that, so let's see. So again, an integral on over m integral over m of d omega is integral of the boundary of m of omega, right? Stokes theorem. And let's suppose that m is compact without boundary. Without boundary, which means what? That integral of the omega over n will be 0, no boundary, right? So the boundary is 0. Now suppose also that omega is closed form on n with boundary, m manifold with boundary. So closed, if you remember, means that d omega is equal to 0, which means what? Which means that integral on the boundary of m omega will be integral of d omega on n and 0 again, right? Very well. Now, there are another particular case would lead us to the fundamental theorem for line integrals, and the particular case of a domain in the plane. So this is for the particular case of a curve in R3. Now, for the particular case of a domain in R squared with boundary, we find Green's theorem here. So just make sure that I do have time to take an example. I will first take an example for Stokes theorem, and there is still time. I'm coming back to see the line theorem and the theorem for line integrals and Green's theorem, how we can pull them out from Stokes theorem. So let me take an example here, and let's take the following example. Suppose that, okay, so suppose that you have a form, a two form on R square, on the sphere, given by x dy wedge dz plus y dz wedge dx plus z dx wedge dy. Okay, something like that. So we would like to calculate, to evaluate integral over s squared of omega. Okay, so let's see how we can find this. So you see, we can look at using Stokes theorem. So we can look at s squared to be the boundary of B3, right? This is the ball in R3 with radius, closed ball with radius 1. You see, what's the boundary of this set? It's given by the triples x, y, z, for which x squared plus y squared plus z squared equals 1. So we find exactly S2. So integral over S2 of omega is using Stokes theorem. This is integral over the ball of the exterior derivative of omega. So let's go and see what is the omega, right? So this will be what? This will be d x dy wedge dz plus y dz wedge dx plus z dx wedge dy. So let's compute this expression. So we have dx wedge dy wedge dz plus dy wedge dz wedge dx plus dz wedge dx wedge dy, right? So this will be equal to, this is well arranged. Now let's look here. I'm moving one, I get a minus. I'm moving one again, I'm getting another minus, plus. So this is the same as dx wedge dy wedge dz. And here I'm switching x and z, I'm getting a minus, and then the z, it's on the second position, I'm switching with y, I'm getting another minus. So I get dx wedge dy wedge dz. So this is 3 times dx wedge dy wedge dz, which means that integral of our two-form omega on s squared is integral over b3 over the ball of the omega, so which is 3 dx wedge dy wedge dz. This is 3 times integral over the ball dx wedge dy wedge dz. But if you remember, this is precisely the volume of the ball. Right? This is how we defined the volume. So at the beginning, was the first thing that we defined when we were talking integration. So this is the ball with center 0, 0 and radius 1, 0, 0, 0 and radius 1. So this is pi, 4 pi, the radius is 1 cube over 3. So this integral will be 3 times 4 pi over 3, which is 4, it's 4, well, 3, so, do I have mistakes somewhere? No, I think that's fine, right? Yeah. Okay, something like that. All right, so this is how we use Stokes theorem. It goes a little bit faster than performing substitution. All right, and because I do have some time here, let me go and see these two particular cases of Stokes theorem, namely the fundamental theorem for line integrals and Green's theorem. So again, Stokes theorem says this: integral over m of the omega is integral over the boundary of m of omega. Now M is an n-dimensional manifold, and omega is an m-1 form on M with compact support. Now, let's take M to be a curve. I'm going to call it C in R cube, and we parameterize the curve as R of t equals some x of t, y of t, z of t, right? And we allow t to go over some interval AB. We define f. We take a function f, a random function. We know that the gradient of f, what we call the nabla f, right? It has components df, partial f over partial f, partial f over partial y, partial f over partial z. Okay, now let's apply Stokes for C, right, for the curve C. So you see, when we parameterize the curve, this is interval A, B, and then you take, this is the curve, this is R of A and R of B, right? So when you parameterize it, right, so I got some water. Now we need a form, right? So we need the form to be, remember, omega is an n-1 form. So in our case, will be in 1 minus 1, right? So this means omega 0, it's a zero form. Right? A zero form, what a zero form is a function, a smooth function. So omega is like this. So it's a function defined on C with values on R, which is smooth. Okay, a smooth function defined over the curve C. So we take omega to be f. So the omega will be the f, and we apply Stokes. So this means integral over, so where did I write it? Here. M is C, so I'm looking here. M is C. The omega will be the f here, right? This will be integral of, what's the boundary of M? Is the boundary of the curve. So R of A and R of B, these are the points on the boundary. So integral on R of A and R of B of f. Okay, but what is integral? What is this? Let's go and calculate. So this will be integral over C. What is df? That's partial f, partial x, dx, plus partial f over partial y, dy, plus partial f over partial z, dz. Okay? So this is what? This is integral, and we can write this as the inner product, the dot product between the gradient, partial f over partial, it's here, right? You can have it here, and dr, right? Which has components dx, dy, dz. Okay, so we have what? We have that this is equal to this integral, but what's this integral? This is simply f calculated on R of B minus f calculated on R of A. So you see, we get that integral over C of the gradient in a product with the R is f of R of B minus f of R of A. So this is indeed the fundamental theorem for line integrals, right? That you are probably familiar if you had a course in this. And then let's take another particular example and try to find Green's theorem using Stokes' theorem. So again, we use this integral over M of the omega is integral over boundary of M of omega. So let's take d omega. So let's take d, a subset of R squared, a region with boundary of D, and we take P and Q, two functions, smooth functions on D, right? So we have D, and we take, and there is a boundary here. Now on Stokes' theorem, we take M to be D, and then we take a form, one form here, right? A one form. So it will be something called form P dx plus q dy. This is a one form, right? And now let's apply Stokes' theorem. So let's see what is d omega first. So d omega will be what? Will be d of p dx plus q dy. Okay, so again, let's go and calculate this. That's for dp, that's partial derivative of p with respect to x dx plus partial derivative of p with respect to y dy wedge dx plus now dq, that's partial q over partial x dx plus partial q over partial y dy wedge dy. So let's evaluate a little bit here. This will be so you have a dx dx, this will be wedge dx, this is 0, right? So this will be partial p over partial y dy wedge dx plus dq partial q over partial x dx wedge dy, and dy wedge dy is 0. Now this is minus dx wedge dy again. So this will be partial q over partial x minus partial p over partial y dx wedge dy. Okay, so this is the d omega. And now let's apply Stokes, right, for these quantities here. So we apply this one. So we have that integral over d of this d omega, which is partial q over partial x minus partial p over partial y dx wedge dy is integral over the boundary of d of omega, which was, if you remember, p dx plus q dy. Okay, but now this is the same as the function here, right? So this is over a domain. So this is simply integral over d of partial x or partial q minus partial x over partial x minus partial p over partial y dx dy, and that's integral over the boundary p dx plus q dy, right? And you recognize here Green's theorem. You recognize here Green's theorem, right? So indeed, this Stokes theorem shows that there's a very nice generalization of and shows us a way to integrate forms on manifolds. Okay, any question here? Questions? Questions?
Yes, Doctor.
Questions, I think, questions? You send, yes, here, can you send a presentation for the 3 days here? Yeah, if I can, is there a way to send files via Zoom?
You can send it to me, Doctor, and I have a group with all students. So
very well, so I will send it to you by WhatsApp, right?
Yes, yes. So I sent it to them.
Yes, of course, I will. Can you send? Yes, because I don't know how to. I'm not even sure it's possible to share files on Zoom. More maybe post? No, I don't think so. All right. Okay, so look, I think. Let me see. Okay, so I'm going to take one more example, and then I think it's enough, right? That was a long lecture. Is it okay? Yes? No?
Okay.
Yes, they said yes. All right, very well. One example, and then you are free. Very well. Let's go and take M. Let's take M to contain all the triples x, y, z in R cube, for which z equals x squared plus y squared, and z is less than 1. Okay, this is a smooth two manifold in R cube, and you are welcome to try to prove that this is indeed a smooth manifold using some results that we present, some method that we presented yesterday. And then let's take the following form here: x dy wedge dz plus y dz wedge dx plus z dx wedge dy is the two form on R cube. And we would like to compute the integral over m of this form. So we want to evaluate integral of omega over m. So we are going to parameterize here, okay? So this is what we are going to do. So we are going to use that integral of omega over m is integral of the pullback of some function that parameterizes over a domain of R squared, okay? So we parameterize. Now, let's see what this function can be. We can define it like this. From 0, 1 times 0 to pi into m. So this would be our d for us by f of r and theta equals r cosine of theta, r sine of theta, and r squared. Okay, so you see this parameterizes indeed our surface. X squared plus y squared will be z, because r squared cosine squared of theta plus r squared sine squared of theta is r squared, which is z, and z will be this r squared, which is less than 1, because it's taken to be between 0 and 1. So you can take here an open interval just to, okay, open interval. Okay, something like that. So that's a good parameterization. Now remember that this must be, so this is a diffeomorphism that it should preserve the orientation. So when you go and compute the Jacobi matrix, right, let's see, partial derivatives with respect to r, with respect to theta. Wait, something's wrong here. Oh, sorry, that's wrong what I'm writing here. That's a diffeomorphism presenting orientation when you compute the rank of the matrix there, right? Then you will get, you get greater than 0. So okay. And so this means that we can say that integral, so we need integral of over m, right? Or the space of omega will be what? Will be integral over the boundary, over d, right? Which is this guy here, over 0, 1 times 0 to pi of d omega. So we need to calculate the exterior derivative of this, of omega. So we'll have what? This is the exterior derivative of, okay, omega is x dy wedge dz plus y dz wedge dx plus z dx wedge dy. Okay, so this is sine of theta in r squared. All right, so this will be what? This will be x, which is r cosine of theta, dy wedge dz. Let's replace everything. So again, make some time. All right, so again, so x, which is, I'm just replacing everything, okay? X is r cosine of theta. Now, dy, so means, this is absolutely wrong with my thing here, okay. So, come on, dy, right? So this is y. The derivative with respect to r, which is sine of theta, dr, plus the derivative with respect to theta, which is cosine of theta, d theta, wedge Can you still hear me? My screen keeps blocking, of course. Okay. Cosine of theta, wedge dz, which is, so this is z, which is 2r dr, plus, so I finished the first one, plus I'm here y, which is r sine of theta, dz, so this is z, this means 2r dr, wedge, like this, dx, this is x, so the derivative with respect to r, this is cosine of theta, dr, the derivative with respect to theta minus sine of theta, d theta, right? And then I'm moving here, plus z, this is r squared, so the z, and I have dx, which is, this is x, so with respect to r, cosine of theta, dr, respect to theta minus r sine of theta, got an r here, right? D theta, wedge, dy, which is this one. So with respect to r, sine of theta, dr, respect to theta plus r cosine of theta, d theta, wedge. I know, I put the wedge already. Very well. Now we need to calculate here. So let's see, equals. So this dr, wedge dr will be 0. So I'm just taking the second term. So I have an r cosine of theta times sine of theta. That's r sine of theta, cosine of theta. Then I still have a 2r here, right? So I get a 2r squared. Now there is no, I'm still, because my screen keeps moving. So this and this will be 0 now. I'm here, right? So I have an r cosine squared of theta. Then I have a 2r, which is 2r squared cosine squared of theta, d theta wedge dr, right? Plus. Now I have an dr wedge dr here, so I'm looking at the second one. So I have this is r sine of theta multiplied by this, that's minus r squared sine squared of theta dr wedge d theta. Now I have an r here. Okay, this is r cube. Then I'm coming here to the last one, right? So I have dr wedge dr, there's nothing. I'm taking this with this. So I have something like this. I have r cube cosine times cosine, that's cosine squared of theta dr wedge d theta. And then I'm coming this one and this one. So this will be minus r cube sine squared of theta d theta wedge dr. Okay, so this will be eventually equal to minus r cube, there is an r cube there, dr wedge d theta. Okay, something like that. So when we integrate, integral of omega over m, this will be integral over the domain of this minus r cube dr wedge d theta. So this will be minus integral r cube dr d theta. R was running 0, 1 and theta 0 to pi. So you can write like this 0 to pi, 0, 1. Okay, so this will be, this is minus r power 4 over 4, 0 to 1 times theta 0 to 2 pi. So that's negative 1 over 4, and that's a 2 pi and it's negative pi over 2. Okay? Questions?
أي سؤال الآن؟ They said no.
So then I think it's enough.
Thank you, Doctor. Thank you for this first part of Riemannian geometry. Inshallah, today we complete with Dr. Mohammed al-Guediri.
Today?
Tomorrow. Sorry, tomorrow.
Tomorrow. Okay.
Allah.
Yeah.
The presentation you can send to WhatsApp. I send to the student, inshallah.
Yes, I will send them right away.
Thank you. Thank you very much, Dr. Liana Topan. Thank you.
Thank you. Bye.
Bye. Thank you. شكرا لكم متدربين.
Everybody.
شكرا لكم جميعا على حضور هذه الدورة الثلاث أيام الأولى من هندسة ريمان مع الدكتورة ليانا توبان عضوة هيئة التدريس في جامعة الملك سعود. حياكم الله جميعا في أمان الله. سبحانك اللهم بحمدك أشهد أن لا إله إلا أنت أستغفرك وأتوب إليك.